So in today's lesson, we're going to continue our discussion about accelerated motion, but we're going to be looking at the position time graphs of accelerated motion, as well as the velocity time graphs and the acceleration time graphs. So let's take a look at, I've presented you with a couple of graphs here. And I just want to remind you before we begin our discussion today that if we look at the slope of a position time graph, then really what we're looking at, what we're calculating, is the velocity of that motion. So for instance, if I were to look at this position time graph, and I can tell it's a position time graph by simply looking at the labels. And you're really going to have to start first looking at the labels before going any further when examining and trying to analyze a graph. So I can see that this is a motion going eastward. Now from this graph, I can tell right away that this is an accelerated motion. Let me tell you how I can see that. I can see that the initial slope of the line, if I were to sort of lay a ruler across here, it's fairly low. It's almost flat at zero. But then that slope increasingly gets more and more steep, so that if I were to place a ruler at the end of this line right along here, then I would see that the slope is quite high, indicating that the speed has increased dramatically. Now let's look at this second graph here and take a minute to think about what's going on here. Maybe pause the video if you want and think about what type of motion might be represented in this graph. So looking at this graph, I can see that it's sort of almost the reverse of what I saw in this first graph on the left. The initial velocity, the initial slope is quite high, indicating that whatever object it is that we're looking at is moving quite rapidly at the onset. And then as time goes by, the velocity gradually decreases as indicated by the slope, to the point where at the end of this motion over here, if I were to lay a ruler across this, I would see that the slope would be pretty close to zero. So this is an object that is slowing down. And so what I want you to do is to examine these two final position time graphs of a motion moving eastward, and I want you to analyze and think about, try to interpret what's going on with these motions. So hopefully you've had time to think about these two graphs and you have an idea about what's going on. So the first thing that I notice is that it seems as though the motion depicted is occurring below the x-axis. So what that indicates to me is that if positive is east for this particular graph, then this object that is moving in a westerly direction. And so initially, the object is moving at a fairly slow speed, but then gradually increases its speed. It is accelerating, but in the westerly direction. Conversely, over here, I'm seeing the object slowing down, but having said that, it's slowing down in a westerly direction because, again, the motion is depicted as being below the horizontal axis. So I hope you did okay with that. If you're still confused, we can definitely bring it up on Monday's class. In fact, now that I think about it, maybe that's what we'll start off with. We'll start off with a warm-up of these graphs of accelerated motion, just to make sure that everybody's on the same page with it. Okay, so moving on, now we're going to take a look at what a VT graph of accelerated motion looks like. But let me first start by reminding you what a VT graph of uniform motion or constant velocity looks like. So, our position time graph would give us usually a VT graph that would look something like this. Let me just try to sketch this out for you. It would look something like this. And, what that's showing is that the object in motion is maintaining a constant velocity for the entire motion. So say, for instance, they were traveling at 4 meters per second, then maybe I would see a 4 here on my vertical axis, and the object would be staying at 4 meters per second for the entire time interval that its motion is being measured. But now, when we're looking at this velocity time graph, we see that the velocity is not staying constant. It is changing, and in fact, it's increasing. And that's not surprising, because with accelerated motion, every single second of the motion, the velocity should be increasing. And so we're seeing that here. So for instance, when I look at this velocity time graph, I see that for the first second, there's an increase of 6 meters per second. Then in the second second of motion, there's another 6 meters per second increase in velocity, and so on. So I can tell from the slope of this graph, of my VT graph, that in fact my acceleration happens to be 6 meters per second squared. Let me try to get this out here. Meters per second squared in a westerly direction. So again, just like the slope of a PT graph will give me the velocity, the slope of a VT graph gives me the acceleration of that motion. So let's take a minute and analyze the units here. If we know that the slope is the acceleration, let's make sure that the units on this graph tell us that. Well, of course, the general formula for slope is asks me to take a look at what the change in the vertical divided by the change in the horizontal, or delta y divided by delta x. Well, let's look at what we're using, what labels we're using for our horizontal and vertical axes. So for my vertical axis, I'm using velocity. And so velocity, I know the change in that would be my v2 minus my v1. And to get my change in my x, I would be looking at my t2 minus t1, right? Or my delta t, my change in time. And let's do a unit analysis of this. So I know that if I look at my velocities and I subtract them, I'm going to end up with units of meters per second, right? That's the unit that we use and that I've indicated on my graph for velocity. I'm going to divide that by units of second. Well, a meter per second is a meter per second squared. And what unit is meter per second squared used for? Acceleration. Boom, there we have it. Slope of a VT graph gives us the acceleration of the motion. So then what the heck is going on in this VT graph? Well, if we think about this in the same way as we would a PT graph, then we're going to misanalyze this graph. We're going to misinterpret it. Let me show you what I mean. Let me get a little drawing going here. So, if I were looking at a PT graph, let me just rough this out, really rough here, right? And I saw a line that was moving that created a line with a negative slope. Then I know that the direction of motion in this negative slope here would indicate that the object is moving in the opposite direction to the motion. So for instance, let's say over here my position was north, then I know that the object was moving in a southerly direction, except for this little mistake here, but this way, that indicates to me that the object would be moving south. However, we can't interpret the VT graph in the same way, right? When we look at this, we know that we're not talking about position, we're talking about velocity, which is analogous to speed. So the speed at the beginning of when the time is being measured is at 24 meters per second, then it becomes, it looks like this is 18 meters per second, then 12 meters per second. So what's really happening here? They're not moving in a westerly direction, they're just slowing down. And that's all that means. Now, what would it look like if I had a VT graph that was depicting slowing down, but then moving in a westerly direction? Well, I would see this line go below the x-axis and into the western region of the graph. So again, really important to look at these labels. A velocity time graph with a negative slope doesn't indicate that the object's moving in the opposite direction. It indicates that the object is slowing down. And that's in line with what we talked about yesterday about negative acceleration, right? This slope here looks like it would give me, let me see, negative 6 meters per second squared. And we know that a negative value for acceleration means that the object is slowing down. So all of that fits together. So just as before, we took the area under our VT graph, and that was able to give us the displacement after a certain amount of time had gone by. So let's take a look at this velocity time graph. I'm going to give it doesn't have an assigned direction, so I'm just going to say that this is east. Okay, we're going to say that this is east, easterly direction. And so let's just, before we begin figuring out the displacement from this velocity time graph, let's just analyze the motion. So what's going on here? What is really, if you had to describe what's going on with this object, in a PT graph, a straight horizontal line with zero slope would indicate the object's not moving. But that's simply not the case when it's a velocity time graph. Instead, you can see that the object is moving. It's moving at a rate of 4 meters per second. What's not happening, however, is it's not accelerating. It's staying at a constant speed. Then all of a sudden we see the velocity time graph kind of dip down. And so what that's indicating is that the object that is in motion is no longer traveling at this constant speed. It's beginning to slow down. It's reducing its speed from that 4 meters per second all the way down to 0 where it's stopping. Now back to this business about figuring out its displacement. And so in this case, we really can't figure out the area in total. So the easiest thing to do is sort of break this figure into two separate parts. And again, that's only if we wanted to find the displacement for the entire time interval. If I only wanted to find the displacement after a certain amount of time, let's say 1 second, I would only look at this area. If I wanted to know the displacement after 2 seconds, I would look at this entire area. But if I want to know the displacement after the entire motion depicted on this graph, I have to look at the area all the way up to 4 seconds, all of this area. But to do that, I'm going to break it up, and I'm going to call this area 1, and I'm going to call this area 2. And so I can think of it sort of like almost like a table of values, right? So I'm going to create a little table of values for myself. And so here's time in seconds. And here is what my position would be. So I'm going to use just D for that. And so at 0 times 0 motion, 0, 0, my position will remain at 0. So I'm going to choose to go all the way to 2 seconds, simply because it looks like this is a whole area that is encompassed by that 2 seconds. So here we go, so 2 seconds. And so area, in this case, the formula that I would use is length times width. So I've got 2 seconds times 4 meters per second gives me a total of 8 meters. So during that first 2 seconds, I've moved a total of 8 meters. So area 1 is 8 meters. Now let's look at area 2. Area 2 is a triangle, and you'll remember, and we haven't seen this yet, I think, this year. So for area 2, I'm going to write this out. So my second area here is a triangle, and so the formula for the area of a triangle, you'll remember, is base times height divided by 2, or 1/2 base times height, whichever you prefer. And so my base here is my 2 seconds times my height, which in this case is also 4 meters per second. And then I'm just going to divide that by 2. Right? So that's going to give me a value of 4. So for this area, the first area, I had 8 meters, and now I have 4 meters over here. And so after a total amount of time of 4 seconds, I've moved not only 4 seconds, but the whole, or sorry, not only the 4 meters, but the 8 meters before it, to give me a total of 12 meters worth of motion. And so I know that the displacement for the entire trip is 12 meters. So my change in position from 0 all the way to the end of the time interval, the 4 seconds, happens to be 4 meters. But what I've also done is I've enabled myself, my bad, 12 meters rather. And since we said it was in the easterly direction, I've moved 12 meters east. But what I've also enabled myself to do is, with this table of values, I could go ahead and I could take that data, the 0, the 2, and the 8, and then the 4 and the 12, and create a PT graph. So let me kind of try to sketch that out to show you what that would look like. Oopsies, there we go. So, 0, 0, again, this is super rough. If this is a position time graph, right? At 0 time, I would just have my first data point there. Let me change the color to red so we can see that a little bit more clearly, right? Then after 8 seconds, after 2 seconds rather, which, you know, if I'm going to split this in half here, after 2 seconds, then I would be at 8 meters, wherever that is, right? And then after 4 seconds, which I'm going to say is about here, I'd have gone 4 meters further, so about half of what I went before. But I need to be careful when I construct this PT graph, and the reason is that I have this motion that's happening at a uniform velocity, constant velocity, and so in a PT graph that looks like a straight line, so that would be a straight line. Okay, but then what I see here is I see that there's some accelerated motion. The object is slowing down, and so because the object is slowing down, the next section, you know, between time being 4 seconds to time being 8 seconds, that's a slow down motion. So how do I show slow down motion? I show the line sort of going faster at the beginning and then sort of curving off and having a zero slope near the end there. So just remember that because there's a straight portion here with zero slope, means that I'm going to have a constant velocity on my PT graph. And then the decelerated motion needs to be indicated by that curved line on my PT graph. So now what I'm going to have you do is a worksheet that will help you to relate the graphs of acceleration time, velocity time, and position time. But before we finish that, what we need to do is we need to take a look at what the AT graph will look like. So going from a velocity time graph to an acceleration time graph, when the VT graph is a straight line, is a lot like going from a PT graph to a VT graph when you have constant velocity. So I know that the slope of this line, remember, is representing the acceleration of the motion. And I can tell from this graph that the acceleration is constant. There's a constant acceleration, and it happens to be 6 meters per second squared. Remember, the slope of the line is representing the acceleration of the motion. And so I know that's the case. So if I'm going to go ahead and sketch an AT graph, it's quite straightforward. You know, I would find my graph paper, and I would say, all right, I'm going to label this. Oops, let me erase that and start over again with that one. What I would see would be if this is my acceleration on my vertical axis and time on my horizontal axis. And since my slope again was 6 meters per second squared, I would find the 6 meters per second mark on my graph, on my scale, and I would go ahead and draw a horizontal line for the entire time interval. So since the time interval is from 0 to 4 seconds, I'm going to assume that at the end over here, this is where my 4-second mark is. And so for the entire time interval, that's going to be a straight line. So again, my acceleration is 6 meters per second squared, which means that every second my velocity is increasing by 6 meters per second, and that's exactly what's being shown on this VT graph. So in our Google Classroom, what you'll find is this handout. It's a worksheet on relating the graphs of acceleration time, velocity time, and position time. And so notice here that I've given you a velocity time graph, and I'm asking you to complete the data, complete the data for acceleration and complete the data for position. And then finally you're going to use that to go ahead on the second side of this sheet. You're going to go ahead and graph both of those in the space provided. So on Google Classroom, what you'll find in addition to this worksheet is the answer key to help you along, to help you sort out how the heck to go about this. And if you have any questions, please save them up for on Monday, and on Monday we will take these concepts up together.